Okay, so maybe we'll do some separable DEs. Oh, I don't know. Maybe we have y prime equals x to the 8th over y squared. This is a separable DE. I can look at it and tell it's separable because I got a lot of experience with these. You might not be able to immediately look at DEs and tell when they're separable, but separable means it's possible to get all the y's on one side and all x's or whatever your variables are on the other. So the first thing we want to do is write this derivative in Leibniz notation, differential form. That's an x to the 8th there. And our goal now is to get at all the y's on one side and the x's on the other. This is not really a fraction. dy dx does not really mean dy divided by dx. This is one unit. But it turns out we're allowed to pretend that this is a fraction. I can multiply the dx over to the other side. I can bring this y squared up to this side and do y squared dy is x to the 8th dx. And it's still legitimate. We're allowed to pretend this is a fraction and multiply the dx over, because now I'm going to integrate both sides. Now, what we're really doing, you'll never have to write this, but what we're really doing is I had this. And now I've integrated both sides dx. And then by chain rule over here, dy dx dx, that's just chain rule. That's just dy. So in a sense, these dx's kind of cancel using chain rule. So that's the math that's going on in the background. But we're allowed to pretend like, well, we're just going to multiply this dx over here and then just integrate both sides. So now we're integrating this side with respect to y and this side with respect to x. Again, we're really integrating both sides dx, but chain rule allows us to get here. Remember, in your life, you will never, ever a single time write an integral without having d something. If you ever find yourself writing this, you're wrong. This doesn't make any sense. I can't take the antiderivative of x to the 7th without having a dx or some differential here. Every time you do that on a test, that's a point off. Always have to have a differential. So here I'm integrating this side with respect to y. So the antiderivative of y squared dy would be y cubed over 3. Technically plus c, but we're going to squish all our c's together on the other side. The antiderivative of x to the 8th would be x to the 9th over 9 plus c. Don't forget your plus c. The plus c comes at the moment when you integrate. Now, you can't wait until the end on these and throw your plus c in. So we would call this implicit form. Because it doesn't say y equals stuff. It's not. And on a test, if it's something handwritten, like a group assignment or something, perfectly fine. Unless the question says put it in an explicit form, this is perfectly fine. In fact, a lot of times it's the best we can do is implicit form. This one, however, we could solve implicit or explicitly. Instead of implicit form, we could put this in explicit form by solving for y. So we could multiply everybody by 3. Now you could here put 3c That would be perfectly fine, but that's kind of weird. This is an arbitrary constant. That's really just a new C. A number times C is just a new C. So I'm not going to do that. I'm just going to call it C. Now, back when I took this class, that would bother me. That drove me nuts. I'd be like, these two C's are not the same. I would go and call that guy C1 and this guy C2. But it's not necessary. Don't stress about that. I'm just going to call this C. I know that that C and that C are different. And I don't care. Now I'm going to take the cube root of both sides because I want Y by himself. So here is my solution. Notice I couldn't just wait until the end and put plus C at the end. Now, here's where this kind of stuff right here matters. Whether I kept that as a 3C or just a C. Whether I changed the name on it. I had these two different versions. These are equivalent, but those C's mean different things. If I were solving an initial value problem, let's make up an IVP. Let's say Y of 0 equals 2. Okay, and here, let's number these. Let's call that version number, we'll call that version 2, and this is version 1. So let's solve the IVP in both cases. In version 1, Y of 0, remember that's your X value, that's your Y value. So that'll be, let's see, 2 cubed over 3 equals 0 to the 9th over 9 plus C. So here I'm going to get C equals 8/3. So then my particular solution would look like this. That's the solution to this initial value problem. If I used version 2, so let's rewrite it so we have it in front of us. It's 9.9. If I use version 2 and I plug in Y of 0 equals 2, so remember that's my X, that's my Y. So I'll get 2 equals the cube root of 0 to the 9th over 3 plus C. So let's see, that's going to be 2 equals the cube root of C. So C will equal 8. I got a completely different value for C. Look, even though I'm using the same letter, that should kind of bother you. It drove me nuts when I took this class. We should really be calling this maybe C1 and this one C2 because they're different. It's not the same C. We got different answers. But here's why it doesn't matter. If I plug that back in here, to the 9th over 3 plus 8. This answer here is the same exact answer as that. Those two are the same. And you could see that. Multiply everybody by 3 here. Solve this one explicitly right here. Multiply everybody by 3. That'll cancel that 3. Take the cube root of both sides. You get this. So if you and your buddy are doing the same problem, you might disagree on the value of C. That's okay, as long as your actual answer is still the same thing. See, the actual answer are still, these are the same. Okay, so anytime you get a number times your arbitrary constant, just rename it. Whatever. 3c, that's just c. E to the c, here's another common. This one's going to happen all the time. E to the c, we're just going to call that c. They're not the same. That's not the same c. Don't care. Like the classic example here is y prime equals y. We could even put in a k value if we wanted to. Like we do this problem when in the applications video. We want some function whose derivative is proportional to the original function itself. This is a separable dE. I could write this as dy dx equals y. I get all my y's to the left side, dy over y, all the x's to the right, and then I integrate both sides. The antiderivative of 1 over y is the natural log of the absolute value of y. The antiderivative of dx is x plus c. That's where the plus c comes in when you integrate both sides. Here's implicit form. If the question says leave it in implicit form, whatever, we're done. But let's write in an explicit form. Let's solve for y. So I can make both sides powers of e. So e raised to the natural log of anything is just that thing. Now I've got this absolute value of y. What I'm writing here, it's not a function. It won't pass the vertical line test. Like if you were to actually graph this, it's a curve in space, but it's not a function. So we're going to have to make a choice here. We're going to have to say maybe what we call this, take the positive branch. So we'll only worry about positive y's so that I can drop that absolute value. The actual solution is going to look like this. Like it's not a function. So I'm only going to take half of it, one of the possible solutions, dropping the absolute value. Now that's a perfectly good solution. I could leave this like this. Or remember rules of exponents. A to the m times n, a to the m plus n is a to the m times a to the n, just rules of exponents. So I could rewrite this as e to the c times e to the x. And then this just looks weird. There's nothing wrong with it. But e raised to an arbitrary constant is just a different arbitrary constant. So I could, there's nothing wrong with me going, okay, I'm going to call that guy C1. And then I'm going to say C1, C2 equals e to the C1. And then come down here and say this. And then circle that. That's perfectly fine. If you want to stress about these arbitrary constants, when I took the class, this is what I did on my test. It's not necessary. You don't have to. If I've got y equals e to the c, e to the x, I can just rename that. And I'm just calling this whole thing here a new c. I'm even going to use the same letter to represent something different. Again, that should bother you a little bit. Let it go. You're going to get used to it. You can only do that with constants, however. Like keep in mind, cx is not just a new c. You can't absorb a variable into a constant. You can absorb constants together, but not a variable into a constant. And really, we've been doing that the whole time. Everything got absorbed. Right here, when I integrated both sides, I really had a plus C on both sides. I just incorporated them all into this one. So this guy absorbed another constant already. Okay, let's do a more complicated separable DE. So let's say we got y prime equals 2x squared y minus xy over y plus 2. Now I'm going to claim this is a separable DE. First, we want to turn that y prime into dy dx. And my goal was to get all the y's on the left side, all the x's on the right. So obviously I could multiply this y plus 2 over, but how am I going to get these y's here over there? When you're dealing with the separable DE, you've got to move stuff around by multiplying and dividing, not adding and subtracting. Adding and subtracting stuff around is not going to help you in general. Like, I don't want to say it'll never help you, but most of the time it won't. I'll show you an example in a minute. Here, I would factor that y out of the top. Now I can take this whole thing there, move it to the other side by multiplying and dividing, not adding and subtracting. So I'm going to multiply both sides by the reciprocal of that thing. So I'll get y plus 2 over y times dy. And I'm going to bring my dx to the other side. Now I've got all the y's on one side, all the x's on the other. And now we can integrate both sides. Now we just got to hope that whatever we wrote down here is something we know how to integrate. Like all those techniques from Calc 1 and Calc 2, you're going to have to remember most of them. I can't think of a single time we're going to use trig sub this entire semester. So don't think complicated stuff like trig sub. But we will be doing partial fractions. We'll be doing a lot of integration by parts, a whole lot of substitution. Like those techniques you're going to be using all the time. Don't make this one more complicated than it needs to be. Remember, you can always split numerators. So I could write this as y over y plus 2 over y, dy. Don't forget your dy. Don't forget your dx. So this is really just the antiderivative of 1 plus 2 over y dy. It's an ugly 2. And then we just integrate. Antiderivative of 1 dy would be y. Antiderivative of 2 over y would be 2 natural log the absolute value of y. And then what do we get here? We get 2x cubed over 3 minus x squared over 2 plus c. There's our plus c. And then this one, I don't even think would be possible to solve explicitly. We're going to be stuck with this implicit solution. Now, we could check this if we wanted to. We could take the first derivative, plug in the first derivative here. Like we'd have to solve that implicitly. We'd have to use implicit differentiation to even find that. Like this would be a real pain to check this solution, but we could if we wanted. Okay, I want to point out one where none of this will work. Looks like a really simple DE. dy dx equals x plus y. This is impossible to separate the variables. It's impossible to get some function of y times dy equals some function only depending on x times dx. Like you might think, oh, well, let me add the or subtract the y over. Like, sure, you could write this. But now how are you going to get this dx over here without touching this guy? If you were to multiply everybody by dx, and again, remember that's pretend multiply, but let's pretend. If you did it, you would get this. Like, we don't have only y's over here. I've still got a dx on the left side. So no matter what you try, it won't work. This guy is not separable. When we separate, we want to do it by multiplying and dividing x's and y's around, not adding and subtracting them. Now, there is a caveat there. If we're in differential form, if I had, I don't know, let's say 3x dy minus 2y dx equals 0. So we're in differential form here. Then sure, like I might add and subtract some stuff around first to make it look like these other problems. Like maybe we'll move all this stuff to the other side. Then I can multiply and divide my x's around. So I'll bring this y over here. I'll bring this x over here. Now I've got it separated. So yes, there might be a little adding and subtracting at first, but to actually move the y's and x's around, you're going to be multiplying or dividing. And then here we can finish this out. What this is supposed to be a 2 here, isn't it? Okay, and then let's see, we'll get 3 natural log the absolute value of y equals 2 natural log absolute value of x plus c. And this could be solved explicitly, but I don't feel like doing it right now. Okay, now let's look at this guy again. Is this also an exact DE? So, or let's see, I'm going to write this in our more standard order with the dx first. Let's check and see if this is exact. Remember, a DE can be more than just one of these. I don't want you to ever get it in your head that a DE falls into one of these categories. Like I could easily give you something that's not separable or exact or linear. Like I could make up something that's none of these, or it might be all of them. Several of these we've done today were not only separable, they were also exact. So let's check and see if this one is. Our M is that stuff that sits in front of dx. And our N is that stuff that sits in front of dy. And we want to check if the partial of M with respect to y is the same question mark as partial of N with respect to x. So we're taking the wrong partials. M is already hanging out with x's. M is the stuff beside the dx. I want his partial with respect to the other variable. Same with N. All right, so M's partial with respect to y would just be -2. His derivative with respect to y, -2. N's with respect to x would be 3. So no, this guy is not exact. This one was exact. It's kind of boring. Let's make up a more complicated exact. Oh, maybe we've got 2xy minus y squared dx plus, it's going to be dy equals 0. I'm trying to make up one, and maybe I shouldn't be doing that. I want an x squared here. And then his partial with respect to okay. Yeah, I think this will work. I just made this up, so I could be wrong, but I think this will work. So the stuff in front of dx, that's what we call m. The stuff in front of dy, we call n. I want to check the partial of m with respect to y. So take his derivative with respect to y. That means x's are just treated as constants. That's going to be 2x minus 2y. So now I'm looking, and I think I did get this wrong. I think I want here minus 2xy. Okay, now I take n's partial with respect to x. So y is just treated as a constant. The derivative with respect to x of x squared is 2x. Derivative with respect to x of 2xy, the y is just a constant, comes along for the ride, that would be 2y. Derivative of 3y with respect to x is just 0. Y is just a constant. Derivative of constant, 0. Those are the same. So this dE here is exact. So what does that mean? That means this dE is somebody's full differential. That means there exists some capital F of xy such that the dE is the differential of f equal to 0, because I've got equal 0 right there. So let's find that. So that capital F must be the antiderivative of m with respect to x. So I am not just, a lot of times I see students do this on a test. They'll take this equation here and they'll just start throwing some integrals around. You can't do that. First off, that's not even allowed. Secondly, that doesn't give you the right answer. We're not just throwing integrals around. We're taking the antiderivative of m here with respect to x because he's sitting beside x. It was his partial with respect to the other guy, his integral with respect to the right guy. Okay, so let's write that out. That's the antiderivative of 2xy minus y squared dx. So let's see, let's integrate that with respect to x. I'm going to get an x squared y minus y squared x, plus possibly, it's possible there's some extra function of y that didn't pop up here. Remember, f depends on x and y. If there were extra y's floating around, they wouldn't have shown up in m. because m is the partial of capital F with respect to x. So if f had some guys that only depended on y, they wouldn't have shown up in m because their derivatives would have been 0. So you got to add in this, maybe there's some extra stuff floating around. Now there are two approaches to go from here. Some books will tell you, now that you've got here, take this guy's derivative with respect to y and set that equal to n. But then you get like, it's like a bunch of extra steps you got to go through. I don't like that method. Here's the way I do it. Keep going. Capital F must be the antiderivative of n dy. N was the guy beside dy. We're integrating with respect to y. So I can't, we got x squared minus 2xy. And then there was that extra stuff that only depended on y. That's where it's coming from. Plus 3y dy. So we integrate this guy with respect to y, and we're going to get x squared y minus xy squared plus 3y squared over 2, plus possibly some extra function of x that didn't show up in n. Now we look at our two answers and we compare. So I'm supposed to have an x squared y and x squared y. Yay. I'm supposed to have this guy. Yay. This said you might end up with some extra things that only have y in them. I did. Oh, there it is. This one said you might end up with stuff that only has x in it. I didn't. This one's 0 because there's nothing left. So now we just squish that all together. Don't add these together. Take everything that's common. Just take everything you see, one of everything you see. So capital F then must be x squared y minus xy squared plus 3y squared over 2. In the homework problems, when they say, tell me capital F, that's what they want. They want you to just type this. But the solution, that's not the solution to the DE. The solution is capital F equals a constant. So in this case, that would be that's the solution to the DE. Why is that the solution? Because remember, the whole point of this being exact is this is an exact differential. Somebody had this capital F and they took the full differential of it. And we have here that full differential equals 0. The only way the full differential of a function equals 0 is if that function was equal to a constant.